Okay, so step one was calculating the basic probabilities. It was gathering information on the frequencies of an event and figuring out the probability of that event happening based on that. In step two, we're going to talk about a concept called the joint probability. Say you flip a coin twice. What are the chances that you get heads both times? What's the probability that you get heads 2 times in a row? The way you see this written in mathematical syntax is with this little upside down U symbol. This symbol stands for AND. Also, every textbook out there will refer to an event like the result of a coin flip with a letter. So you'll see this written as, what's the probability of A and B? A is getting heads on the first flip, and B is getting heads on the second flip, in our case. If probability is a new topic for you, then maybe just quickly pause the video and figure out what the probability is of getting heads 2 times in a row. Did you have a go? If so, how did you figure this out? What was your approach? One way that you can solve this kind of problem is to draw a matrix. This matrix has all the possible combinations in it. And there you can see that there's a total of 4 possible outcomes with the coin flipping problem. From our little chart here, we can see that both coins showing heads only happens 1 in 4 times. So therefore, the probability of getting heads on 2 flips in a row is 25%. But you know what? There's a better way to calculate a joint probability. All we have to do in our coin flipping example is to multiply the probability of getting heads times the probability of getting heads. Since we have a 50-50 chance of getting heads, it's 0.5 times 0.5, which is 0.25 or 25%. In other words, we're multiplying the probability of A times the probability of B. And that's how we can get the probability of A and B. Now, I think this formula is really, really handy when you don't want to draw a huge matrix. Because say you want to calculate the probability of getting heads on a coin flip 4 times in a row. Well, simply by applying this formula, you know it's 0.5 times 0.5 times 0.5 times 0.5, which is equal to about 6.25%. So now let's use this technique with a dice. Pause the video and, as a challenge, work out the probability of rolling a 6 on a dice like this 3 times in a row. Did you have a go? With a 6-sided die, you essentially have a 1 in 6 chance to roll any particular number. So rolling a 6 3 times in a row has a joint probability of 1/6 times 1/6 times 1/6. And that's equal to approximately 0.46%. So less than 0.5%. Very, very unlikely. Now, I know these were some very, very simple examples just now, but I hope you can see how rolling more and more 6s in a row gets less and less likely. And the same with flipping coins, right? It would be strange to see somebody get heads after heads after heads after heads on a fair coin, that is. Now, I think personally this is like the very friendly and simple side of probability, but it's still interesting. Because let me ask you a question. Imagine you and I are hanging out on a Friday night, chilling, flipping coins and talking about probability as we do. And I've just flipped my coin twice. Both times I got heads. What's the probability that I get heads on my third flip as well? Is it 1/2 times 1/2 times 1/2 or 0.125? No. It is not. Most definitely not. And the reason is that the past coin flips don't affect the next coin flip. Each coin flip is independent. the probability of me getting heads on that third flip is still 50%. Now, this might seem obvious to you, but intuitively, I've seen a lot of people just sort of accept this idea of independence. Intelligent people too. It's like, people don't want to accept this. And if you don't believe me, you can actually observe this behavior for yourself. All you need to do is go to a roulette table in a crowded casino and just wait and watch. Just watch people. Now, if you've never played roulette or you're not familiar with this game, in the casino, people spin this wheel and people win when they've predicted where the ball will land. People can bet on a number of things, but they can also bet on the colors, right? The color that the ball will land on. So in this game, a lot of people love betting on a particular color, right? Red or black. Will the ball end up on the red or on the black, for example? Now, when the ball has been landing on black for a few times in a row, you will see that people increasingly start betting on red because they think it's the more likely outcome for the next spin. Intuitively, many people think, hey, it's been black 4 times in a row. On the next spin, the ball just has to land on red, right? But the truth is, red is not more likely. Why? Because each spin of the roulette wheel is independent. The wheel itself doesn't have any memory of the previous outcomes. Okay, so that's a real-world example of this concept of independence in action. And we've actually covered quite a few important concepts in probability so far already. We've covered basic probability, which was very much based on observing the frequency of a particular event. We've covered this idea of independence, where 2 events have nothing to do with one another. And finally, we've also covered this idea of joint probability. And what we saw was that for independent events, like rolls of dice and coin tosses, the formula for both A and B happening was simply by multiplying the probability of A times the probability of B. Now, let's take this discussion back to spam classification. In order to work out the probability of an email being spam, we should look at something other than the frequency of spam emails out there in the wild, right? We should look at the contents of each individual email. This means looking at the message itself, which is, well, where it gets interesting. Now, if you fire up Hotmail or Gmail right now and you look through your email spam folder, what kind of words do you tend to see in the message bodies for these emails? I bet you can kind of spot a pattern. You can spot certain themes coming up over and over again in your spam emails. Certain words are just much more likely to come up in spam email than in regular legitimate email. I'm thinking of words like free, access, Viagra, loan, online pharmacy, adult, great offer, winner, casino, Bitcoin, what have you. Like, when was the last time a friend of yours sent you a legitimate email about an online pharmacy or free Bitcoins, for example? So clearly, there's going to be a clue in the message body whether an email is going to be a spam email or not, just purely based on what the email's about. So imagine a new email arrives in your inbox. The email body contains the word Viagra. Should this email be classified as spam? Let me rephrase that question. Given that this email contains the word Viagra, what's the probability of this email being spam? This question that I just posed is all about conditional probability. And this is where things are going to start getting pretty wild. Conditional probability is, in my personal opinion, both something unintuitive and difficult. And we're about to get our hands dirty with some of these meaty statistics. Oh yes. You see, this is really, really worthwhile doing, actually. Many of the basic statistical concepts like probability, independence, joint probability, and conditional probability are used everywhere in machine learning, even if you don't see it right away. Even our box standard linear regression models come straight out of a statistics textbook. The nice thing about the naive Bayes classifier is that we don't use statistics and probability under the hood. We're going to use probability explicitly. Our naive Bayes algorithm uses statistics in its raw and pure format to classify email spam. And conditional probability is at the very heart of it. Conditional probability measures the probability of some event given that another event has occurred. The mathematical syntax looks like this. What we have here reads the probability of A given B. For example, what's the probability of me getting heads on my next coin flip given that my last coin flip was heads? Well, we just talked about this. The first coin flip doesn't affect the second coin flip, so the two events are conditionally independent. The probability of me getting heads on that next flip is still 50%. But, what if the two events are in fact dependent? Going back to our email example, what's the probability of an email being spam given that it contains the word Viagra? In this case, the probability of the email being spam actually depends on the probability that the email contains the word Viagra. What? That sounds weird, right? Now, I don't expect you to accept this at face value. Let me try and explain this with a different example where the intuition is less murky, it's much more clear. Say you look out the window and it's cloudy outside. What's the probability of it raining today? In other words, given that it is cloudy, what is the probability of rain? Now, in this picture, it looks like it's about to rain any minute, but why rely on eyesight when you can have a mathematical formula? You see, like all good things, conditional probability has a mathematical formula associated with it. And here it is. The probability of rain, given that it is cloudy, is equal to the probability of rain and it being cloudy divided by the probability of it being cloudy. Okay. This looks like a very, very strange formula indeed. But the important learning point here is that the probability of it raining depends on the probability of it being cloudy. And that's the bottom part of the fraction here. The bottom part of the fraction is the probability of it being cloudy. If it was cloudy for 250 days a year last year, then this part of the fraction is 250 divided by 365. Now, what about the top part of the fraction? Well, guess what? This is our old friend, joint probability. It's the amount of overlap between the days that were cloudy and the days that it rained. So in London, it rains on approximately 107 days per year. But you know what? 2 of those rainy days were actually fairly sunny and I saw a rainbow. So the number of days where it was both raining and cloudy was only 105. So the top part of that fraction is going to be 105 out of 365. Now doing this calculation gives us a conditional probability of approximately 42%. The probability of it raining, given that it is cloudy outside, is 42% according to this formula. I know this may sound a little bit trivial, but the really, really cool thing is that what we've just done is calculate the probability of something knowing something else. And that sounds a lot like fundamental machine learning, right? Knowing the movie budget, we can calculate expected movie revenue. Knowing the number of rooms, we can calculate the expected property price. Think of it being cloudy outside as a feature, and think of it raining today as your target, your why. So I hope this example shows how conceptually conditional probability is actually widely applicable to machine learning. And if you open any statistics textbook out there, you'll see that conditional probability is expressed in very general terms, just like this. The probability of A given B is equal to the probability of A and B over the probability of B. What would this formula look like in our spam example? Substituting for A and B, we get something like this. The probability of an email being spam, given that it contains the word Viagra, is equal to the probability of an email being spam and the probability of the email containing the word Viagra over the probability of an email containing the word Viagra. Looking at this formula, there's one problem though, and that's the top term in this fraction, the joint probability. Calculating the joint probability was super easy when we were dealing with dice and with coins, because each event was independent. In that case, we could just multiply the probabilities of the events together. But with dependent events, like clouds and rain, or email and the word Viagra, this calculation is no longer so simple. And that's why, to calculate the conditional probability and create our spam classifier, we have to take it to the next level. We have to use Bayes' theorem.